So let's see one application of this F-factor theorem. By using this F-factor theorem, we can characterize all possible degree sequences of the graph. Let's say a list or sequence T1 to Tn is graphic. So graphic list or graphic sequence is if it is the degree list of some graph. So for example, if you say 2, 2, 2, 2, 2 is a graphic sequence because there exists a graph, say 5 cycle, whose degrees are all 2. But on the other hand, if we say 2, 2, 2, 2, 1, then we know that any graph has degree sum even. So its sum is odd number, meaning that it's never a degree list of a graph. So this is not graphic. Then the question is, what list is graphic? What kind of sequence can be a degree sequence of a graph? Obviously, it has to sum to even number, but is it sufficient? Let's say if you have 100 and then 0 and 0, then obviously it's not possible. There should be 3 vertices and one vertex has degree 100 and the other one is 0, 0. Of course, it can be, if you consider multigraph, then you add loops, so it's okay, but otherwise it's not. So there is this theorem by Erdős and Galai. Non-increasing function. Non-increasing, non-negative integer T1 to Tn is graphic if and only if the following holds. So first, the summation of all the numbers must be even, and for each k we have the sum of k numbers, k largest number is at most k times k minus 1 plus summation of minimum k and d sub I for all the later number. If this holds, then we can conclude that the sequence is graphic. So how can we prove this? If we have D1 to Dn, and this is a list of numbers, and we want to show that whether this is graphic or not. But this being a graphic means that let's say f of vi is ti, and this defines a function f. And then we consider a n-vertex complete graph, Kn, with vertices v1 to vn, and then let f be the function that f of vi is ti. And if this complete graph has an f vector, then there exists a graph with degree sequence d1 to dn. So these are equivalent. This degree sequence being graphic is same as that complete graph on n vertices has an f vector with this specific f. And we know when a graph has f vector. So we just proved the f vector theorem. So we can illustrate this into other condition. And then we can check whether this other condition that's equivalent to, the existence of f vector is restated in this given condition. So that's what we should check. So for that to check, in f vector theorem, we have the condition which looks in this way. So for given S and T, we should have this inequality. In here, F, D, F are somewhat tractable, but this Q, the value of this Q is, more complicated than other. So we want to know how to compute this Q value in our situation. But in our situation, we have complete graph. In complete graph, even if we take S and T, the remaining vertices form only one component. So this QST must be either 1 or 0. So we need to decide whether this is 1 or 0. We already know this is 1 or 0, and then we need to decide which one is our answer. To decide whether this is 1 or 0, we only have to consider its parity. If this is even number, then it must be 0. If this is odd number, then it must be 1. So let's prove a lemma which solves our problem of determining this Q value. So for any this given non-negative function f, we can actually predict the parity of this Q through this lemma. Let's say we have this joint vertex sets S and T. Then QST plus FT minus degree of G minus ST minus FS. We know that this has the wait, is it still recording? Same parity as f value of the entire vertex set. Let me check whether it is still recording. Wait, it's not recording. I'm not quite sure whether it's keep recording. Let's see. If it is not recorded, then I have to record it again. Anyway, so we want to show this lemma. This expression and the, some of the f values of the vertices in G have the same parity. So from that, we can actually predict the parity of this Q. So let's prove this. So that R is the vertices outside of S and T. Then QST counts the component Q in G minus S minus T such that f of Q plus the number of edges in G between Q and T is odd. So what do we know is this QST has the same parity as FR plus the number of edges between R and T. This is because we have S and T and R. We have several components. And each component, we say this is G of Q. Then G of Q counts number of edges between them and then the F value here. So G of, say, C1, G of C2, and G of CS. If this is odd, this GCT value is odd, then we write 1. If this is even, then we write 0. And if this is odd, then we write 1. And we sum up these 1s, then that's exactly QST. So parity-wise, it's same as just adding all the G value is just taking F of C1 to F of CS, and then E of the number of edges between C1 and T to number of edges in CS and T. This is exactly same as number of edges in RT, between R and T, and this is same as the F value sum in all the vertices in R. So this expression has exactly the same parity as QST, because it's the summation of all these values. So also, if you count the number of edges between R and T, and then we add the degrees in G minus S of the vertices in T, then we have R, T, and these are all counted. And then in this expression, these inside edges are counted twice, and then these edges are again counted. So this actually counts 2 for each edge inside T and each edge of this cut between T and R. Thus, what do we have? This expression that we want to get the parity of has actually the same parity as FR plus ERT. So instead of QST, we can change to this, because these two expressions have the same parity. And then we have FT and DG minus ST minus FS. And here we show that, this and this together counts 2 for each edges. So here we have plus and minus. You can just change plus and minus freely when we consider just the parity. And then this is even number. And what's the other three? This and this and this. R and T and S. It's F value sum of the vertices in R and T and S. So which constitute all the vertices. So it's F value sum of the all vertices. And then these together is even. So it has same parity as the F value sum of the entire vertices. So this proves the lemma. Now let's prove the theorem. So let's prove the necessity. So if this is graphic, then this has to satisfy. If this is graphic, then there are graphs with that degree list. Then what you do is you take k vertices of the highest degree. So there are k choose 2 edges, say at most. At most k choose 2 edges among k vertices of highest degree. And each remaining vertices contributes at most k and at most its degree to the degree sum, which means that if we take I from 1 to k, this is that you take the k highest degree vertices. This counts all the edges inside twice. So this edge is counted twice with respect to this left vertex and with respect to this right vertex. And then these edges from this set to outside is counted once. But these edges, these crossing edges, we can count in other way. How? For each vertex, you count the number of edges between this vertex and this set S. So, vertex inside is counted twice. And then for each this vertex, say vk plus 1 to vk vn, you count the number of edges between this vertex and this entire set S. So S has size k, so this is at most k. Also, if some vertex has degree low, so this vi has degree di, which is smaller than k, then you can send at most di edges to S. So we have minimum of k and di. So this inequality must hold. So now we show that sufficiency. So as we mentioned before, let vi be f of vi be di, and consider a copy of complete graph on n vertices with vertices v1 to vn. We proved that this has an f factor. Then what do we know? If we take vertex at S and T, and if we delete S, then the degrees of any vertex becomes n minus 1 minus size of S for each, say, vertex in T. Then touch F factor condition becomes, so what was the touch F factor condition? Let's go back. So this is the condition. This becomes, say, we have ft. Let's write the other things on the other side, fs. And then this part become plus degree in g of s minus t, but which becomes, which is same as every vertex has degree n minus 1 minus s. So this becomes m minus 1 minus s, and then number of vertices in T, then minus QST. So we want to show that, so it suffices to show, say, this double star holds for all ST, disjoint set. So let's get rid of this QST first. Since Kn minus S minus T is connected, QST is at most 1. Moreover, we know that F-value sum is even. The previous lemma says that QST is also even. So it must be 0. Give me a moment. So let me check the lemma again. The lemma says that this has the same parity of this. And yes, so let's take this box. So the lemma says that we have this QST minus Fs. So this has the same value as n minus 1 minus S times T minus QST. So because lemma says that if you take this expression, then it has same parity as the F value sum, which is even. So that means these two expressions, this expression and this expression have the same parity. And if we know that this holds, if this holds, and further QST is 0, then automatically we get this desired one. So we are done. And if we know that this QST is 1 and this holds, this inequality holds, then once we subtracted it, if this is violated, so before subtracting it, this was not violated, but now we subtract 1 if this suddenly becomes violated. Then that means that previously this was same, but now you subtract 1 and this is not satisfied. But in that situation, this right-hand side is just 1 smaller than the left-hand side. So these two must be having different parity, so which contradicts the lemma. So this concludes that as long as we show this inequality, then we are done. We automatically get this double star inequality. So let me summarize again. So let's say not this. So it suffices to prove ft is at most fs plus n minus 1 minus s times t. Because we know that this number and this number has the same parity, and this q value is at most 1. So if this inequality holds, and then right-hand side is at least 1 bigger than left-hand side, then once subtracting it, it is fine. And if this holds with the equality, then, then the QST must be 0. Because otherwise, you subtract QST, which is 1. Then before it was same, but now, this right-hand side becomes 1 less. This is 1 less than left-hand side, so they have a different parity, which contradicts the lemma. So it suffices to just prove this inequality. So let size of t be t, and size of s be s. So we want to show that this right-hand side is bigger than summation of degrees. So f value is degree of the k largest one. Let's say this is k. Then it's natural that whatever t you take, its f value sum is at most the sum of k largest number. So we want to show this. For that, we take fs plus n minus 1 minus s times t. And this is summation of at least the smallest s numbers sum. So this is the f value sum of the vertices in S. So several numbers di. It's sum of the several numbers in di. And then you take the smallest one, then that's lower bound. And this is n minus 1 minus s times k. So this is same as n minus 1 times k plus s numbers of k, so summation of di minus k, where I is equal to 1, from n plus 1 minus s to n. So here we have the several degrees. So let's say this is k. So t1, t2, t3, t4, t5, t6. You have some numbers above k and some numbers below k. In this right term. On here, these are negative. On these vertices, di minus k is negative. And on these vertices, this is positive. Then what's the lower bound of this? You collect all the terms which give us negative and then add together, then that's as negative as possible. If you just add that, okay, this is say negative 1, negative 2, negative 3, negative 4, then if you add only 2, then you get negative 7, which is not enough. So you just add all together to get negative 10, which is the smallest. And you don't want to add any positive side because it will make it less negative. So, to indicate this point, let S prime be the maximum such that m plus 1 minus S prime is bigger than k, and degree of m plus 1 minus S prime is smaller than k. So this second condition spots that from here, so there are S prime many vertices which give us this negative value of di minus k. Then what's the first condition? First condition is that we are later taking the k vertices with the highest degree as t. But when we take S, we don't want to take the same vertex as t. We want to make sure S and t are disjoint. For that, we are going to take the vertices with the smallest degree as S. So for that to be disjoint from t, we have to add this condition. So maximum S prime satisfies this. Then this is actually at least n minus 1 k plus summation of I equal n plus 1 minus S prime to n di minus k. We only collect the terms which are negative, while S is not taking more than n minus t vertices, n minus k vertices. Then you can collect all the, this you divide it as k times k minus 1 plus n minus k times k plus this summation. And this is same as k times k minus 1 plus summation of I from k plus 1 to n k plus summation of n plus 1 minus S prime to n as a di minus k. So what's this term? So it's all k, but from this point is exactly where the di is smaller than k. So this is actually, you can check that this is minimum of k of di, where ki is from k plus 1 to n. But what did the condition in this theorem says? This expression is at least as big as the sum of k largest degree. So whatever t we take, whatever k vertices we take as a t, we get this inequality. So this star is satisfied, holds for any st. Hence, this double star also holds by the previous explanation. And F-factor theorem says that the complete graph on n vertices has the corresponding, the desired F-factor. So this proves the theorem. So today we learned about the F-factor theorem, and then we learned one application of this to graphic degree list. And next time we will learn more about the matchings. So thank you for listening.